You're listening to the FQxI podcast. Today.
But what's fascinating about this result is that it suggests that gravity is more like this idea of a regular force.
We conclude our countdown of this year's biggest stories in physics.
And your own conspiracy theorist would say, oh, there must be aliens. And in that case, there would be. There'd be humans.
As quantum physicist Ian Durham reveals his number one highlight of 2022.
Just proving that it's possible that human beings could actually do this. And this is where I'm going to get a lot of flack. I know I'm going to get a lot of flack for this one.
I'm Zeeya Merali. Welcome back to the final part of the special podcast series from the Foundational Questions Institute, counting down the top physics advances of 2022. Quantum physicist and FQxI member Ian Durham of St Anselm College in New Hampshire is still with me, and he's continuing to pick out his top 5 results of the year. On previous editions of this podcast series, he announced some of the runners-up and the advances coming in at numbers 5 and 4. If you want to listen to those, you can find parts 1 and 2 of the countdown on the podcast page fqxi.org/community/podcast, where I'll also be linking to more information about all of the research described today. Now, I should warn you that part of this recording was made during that intense winter storm that hit parts of North America while Ian was in Buffalo. So for a short period, you may hear some interesting background noise, which I've tried to remove as far as I could, but please bear with us, it does improve again after a few minutes. So, now, over to Ian. We're getting close to the number 1 spot. What comes in at number 3?
So, coming in at number 3, there's a really awesome result. They experimentally proved that there is a gravitational equivalent to the Aharonov-Bohm effect. The Aharonov-Bohm effect in electromagnetism is this weird thing. So particles can feel the influence of electromagnetic fields that they don't come anywhere near.
The electromagnetic Aharonov-Bohm effect was predicted in the mid-20th century and has been demonstrated in the lab.
The classic example is like you can create a magnetic field with a solenoid. So basically you twist wire into a loop. So it's this long coil of wire that inside you have a very strong magnetic field, but you can show that there's no magnetic field on the outside of this thing. But if you fire charged particles near this thing, they'll respond as if they knew the magnetic field was there, even though the magnetic field isn't there. Like it's there, but it's inside the coil, and they're outside the coil, but they somehow can react to the presence of the magnetic field. That's the classical Aharonov-Bohm effect, which is named after Yakir Aharonov, who I think is an FQxI member, and David Bohm, the late David Bohm.
Yes, indeed, Yakir Aharonov is an FQxI member, so yay for getting onto Ian's list. And of course, when you say that this is the classical example, Ian, you mean in the sense, just to clarify, of it being the classic archetypal version of the experiment that has been demonstrated many times already. But it's not a classical effect. It's quantum weirdness about like the fuzzy locations on a quantum level that mean that classically, even though you would think particles that are traveling around the coil in a region where they shouldn't feel any field wouldn't be influenced, really it's because they are in a superposition of being in more than one place at the same time, and somehow they are still influenced by it.
How you detect, by the way, in the classical electromagnetic, it's not classical, it's quantum, but in the electromagnetic case, how do you detect the Aharonov-Bohm effect, right? How do you know that atoms have seen the magnetic field that's inside the coil, right? Is, you fire them so that they take 2 different paths one going around one way, one going around the other way, and then they interfere with one another on the other side. So it's an interferometer experiment, right? So you're basically getting an interference pattern, and the interference pattern is only there because the magnetic field is there. It wouldn't be there if the magnetic field isn't there, because what happens is they respond to the magnetic field, even though they're not in the magnetic field.
So what's the new part? How does gravity come into this?
This year, there was a group that did an experiment that showed that there was a gravitational equivalent to this. One of the lead people on the experiment was a guy at Stanford University named Mark Kasevich. And what they did was they launched rubidium atoms inside this. They had this 10-meter tall vacuum chamber. They'd hit the rubidium atoms with lasers, which would put them in a superposition of tracing two different paths. And then they'd let them fall. So they're tracing two different paths through this vacuum, but it's a superposition of two different paths. And they watched how they fell. But, they're falling in an actual gravitational field.
So I should say that regular listeners will know that I interviewed the lead researcher behind this result, Mark Kasevich, on the podcast back in March. And there's an extended version of that interview on the podcast page, fqxi.org/community/podcast, where we talk in some depth about all the clever lengths that his team went to try and account for the effects of the gravitational field. It's honestly really worth listening to the long version because they use some very cunning tricks.
You can't completely isolate yourself from gravity. Everything interacts gravitationally. But what you can do is you can do clever tricks to work out, gravity under normal conditions should have, say, this particular effect on something, right? And so you can then run your experiment in such a way that you can filter out the effect of these expected gravitational forces, and then if you see anything beyond that, then you're seeing something. In this case, it's the Aharonov-Bohm effect. Essentially, at the top of the vacuum chamber, they had this mass of about 1.25 kilograms of tungsten, okay? If you do the experiment with that mass and then without that mass, and you have these pairs of atoms, right? And you launch it so that one flew close to the mass and the other flew lower, and you split each of them into superpositions, and one path is always traveling closer to the mass than the other, and they're separated by about 25 centimeters. And they did this with lots of different paths, and they could basically do it with and without the mass. They could compare how the various sets of atoms interfered, both with and without the tungsten mass.
And then they're looking for the same sort of interference effect that you usually see for particles moving around the solenoid in the electromagnetic example you gave.
Same sort of thing here. You're kind of using the mass as sort of like a stand-in, and you do some experiments with it, and then you do it without it, and see if there's a difference. And if there's a difference, then it's basically you've seen a gravitational equivalent of the Aharonov-Bohm effect, which is just weird.
So you've described the experiment, and it seems really exciting and interesting. And as I say, I interviewed Mark Kasevich, and it's such a clever setup. But we know that this was something that people have been predicting might be true for gravity. What's the particular relevance of actually now having demonstrated it? Is it telling us anything we didn't already know?
Yeah, so this is really interesting. I think this is the most fascinating part of this experiment. So if you understand general relativity, according to general relativity, gravity is not really a force per se, like the other forces. It's the curvature of space-time. So it sort of has this difference. In the standard model of particle physics, we assume that if eventually gravity will fit in as one of the forces of nature, that it will behave in a similar way in that there will be a carrier particle, in this case it would be called the graviton, and that sort of thing. So you've got these two ideas. You've got this quantum idea that gravity is just like any other force, and then you have this general relativity view that it's not really a force at all. It's this curvature of space-time. The question is which one of those is it? The full answer is that we don't know yet. But what's fascinating about this result is that it suggests that gravity is more like this idea of a regular force. The gravitational field behaves more like a standard like electromagnetic field. So the fact that we see this effect with gravitational fields is extremely suggestive that there's a correspondence there, and that, yes, just like electromagnetism and the strong nuclear force and the weak nuclear force, gravity is a force just like those others are and has similar kind of behavior. Well, is general relativity wrong? Well, no, of course it's not wrong in the sense of, we rely on the general relativistic equations every day to make sure that the GPS system works, et cetera, et cetera. But it suggests that the interpretation of it as a curvature of space-time may either be incorrect or may be incomplete, because then the question becomes, okay, maybe it is the curvature of space-time, but maybe space-time now develops a sort of an ontological status unto itself that maybe in some interpretations it doesn't have, meaning that it possesses the properties of a field in that sense. And again, these are open questions, but what's intriguing about this particular result is that it nudges us in one particular direction. It says, yes, gravitational fields do behave very much like electromagnetic fields in this particular case, and therefore it suggests that it's like a real thing. It's not just the curvature of space-time.
Wow, okay. So, I mean, that's a very deep thing to say. And it strikes me that I haven't really thought about how deep it was before until you started to bring in, what this actually tells you about space-time. Because if we are talking about the four fundamental forces all being very, very, very similar in nature then, and they all have a carrier particle, and like you said, the electromagnetic force has the carrier photon and gravity has the graviton. We've talked about this on the podcast before. You and I have talked about it, and other researchers have. But it doesn't explain why gravity would then be masquerading as this curvature of space-time, or why it is the one that has a special relationship to space-time. And we don't see an equivalent relationship with electromagnetism to something else. It just seems very, very perplexing.
Yeah, so I would say, or does it, in regards to the electromagnetism thing? Maybe it does have a special relationship to something else that we just don't know of yet. I don't know. I think, and I've long struggled with this. I've long struggled with this problem. In fact, going back to my PhD thesis, because my PhD thesis was on Arthur Eddington's fundamental theory, and which is him struggling with it. About 100 years ago, he struggled for the last part of his life about this very problem. These are really deep questions, and they're old questions. They go back, 100 years.
Let me ask you then about something we spoke about earlier in this conversation, which was also about relating gravity to sort of quantum theory. And that was the duality, the equivalence, the conjecture that related space-time and gravity in a certain kind of imaginary, hypothetical, mathematical, abstract space to the behavior of particles governed by quantum theory on that space's boundary. And we spoke about that in terms of wormholes. And one of the reasons we mentioned that people are so excited about that correspondence is because it provided some sense in which gravity and quantum stuff are equivalent. They're sort of two sides of the same coin in a way. Wormholes could be the same as entanglement in some sense. Now we've also got this picture where everything is the same type of thing. Gravity is just the same as electromagnetism and the strong force and the weak force, and it's mediated by a particle. Is that complementary to that kind of ADS-CFT duality picture, or is it in tension with it, where on the one hand everything is the same, and on the other hand two things are equivalent but very different in nature, but somehow equivalent, dual, identical?
So that's a really, really good question. And oh boy, I'm inclined to say that I don't know. I think it could go either way. I think it could be either that this is maybe a tantalizing glimpse into true ADS CFT correspondence. So, but I don't know if anybody's actually tried to couch either of these in ADS CFT terms. But maybe this is a push in that direction, or it is maybe just a nudge in this direction of gravity just being like all the other forces. But then, as you point out, we would have to explain the wormhole thing. I mean, I could imagine that we can simulate wormholes, but I could imagine a universe in which wormholes actually don't exist, even though they are allowed by the math of general relativity. Just because something's allowed by math doesn't make it real. Please don't tell Max Tegmark that, but hopefully he doesn't listen to the podcast. But so it's possible on the one hand that gravity is just a normal force and that the general relativistic sort of thing, that this curvature of space-time kind of thing, is just a convenient mathematical tool. On the other hand, I could also imagine a universe in which someone looks at this experiment and discovers that it's further support for ADS-CFT. I don't know. I think it's a really, really good question, and I don't know which is the more interesting answer, to be honest. And I've never been a big fan of ADS-CFT, but part of me wonders if the ADS-CFT answer isn't the better one, or the more interesting one.
Well, at least wormholes got into the countdown somewhere. But I want to ask you about how this kind of setup might be used for other foundational investigations.
Let's talk about Big G first. Big G is Newton's gravitational constant. Actually, already mentioned it once on this podcast. The standard Newtonian force between two gravitating objects is F equals big G, mass 1, mass 2 over the square of the distance between them. So why would we want to measure big G to really, really, really high accuracies? Well, in order to keep the GPS system really, really accurate, so to improve the accuracy of the clocks on the GPS system, you have to really, really understand exactly where they are and their location, because it's all about timing signals. The more accurate you have for the distance between the satellites and between the satellites and the ground, the more accurate you synchronize your clocks and the more accurate you can pinpoint something. I'm more of a theorist, so, in a lot of cases, I just approximate G is equal to 1. I do that with a lot of constants.
Don't start that. Don't bring that up for our listeners. Listeners who understand that will be fine with it, but for other people, don't worry about it.
Yeah, just ignore me.
Don't worry about theoretical physicists making everything equal to 1.
Yeah. So what could we do with this? So there are a couple of things. One of the interesting things you could do with this experiment is you could do a test of the accuracy of clocks. How clocks are affected by gravitational fields. When we talk about a clock, right, we're talking about anything that has some kind of regular periodicity to it. The whole philosophy of clocks is deep and interesting, but essentially that's what they are. So we know in gravity, just classical gravity, that clocks run at different speeds in different gravitational fields. So this is the issue with the GPS system, right? So the clocks on the satellites run at different speeds than the clocks on Earth. And in fact, they run at slightly different speeds from each other. You can even show that. So in fact, if you have a cell phone, depending on what service you use, if you're outside of North America and you're using the GSM protocol, your cell phone is actually getting its time, this GPS system, not from the cell phone towers. And in order to do that, it has to correct for relativity. And if it doesn't, it can be off by quite a bit. But then you can also have weird quantum things. There have been a number of groups that have studied entangled clocks, including Czaslaw Bruckner, who's with Anton Zeilinger in Vienna. Turns out gravitational fields degrade entanglement, for one. And so I could imagine that this would be an interesting test bed for looking at the behavior of clocks in these types of situations, because you could put the clocks in a superposition of different paths and then see how they respond to the presence of the gravitational field.
Well, you've brought up time and clocks. Is this a good moment to maybe gently tease something that might be happening in the new year?
Sure.
I know that our listeners love you, Ian. I know that we have a bump in listeners for this end of year review. If any of you would be interested in maybe taking an online class with Ian to find out about the nature of time, it's something he has taught before. It's something he's been researching before. It's something that, well, as I understand it, his thinking has grown out of an FQxI meeting on the nature of time. Then I would say, let me know, or let Ian know. Probably the best thing to do is to email me at podcast@fqxi.org. We don't want to say too much about it, but I would say, if you send me an email, we'll put you on a list. We'll make sure that you hear about it if and when it starts up in the new year. It's very much in development, so we want to know if this is something you would be excited and interested about potentially attending.
So I teach a class on the nature of time, the origins and nature of time at St. Anselm, retitled it Time from Consciousness to Cosmos recently, I guess. I'm working on a book on it. It all grew out of a FQxI conference in 2011 on the nature of time. Half of it was on a ship in the North Sea, and the other half was in Copenhagen. It was a great conference. And I've been thinking about time ever since that conference. And so I've developed an entire course that I teach on it. I've actually got 2 books. I wrote a book that I use it as sort of a in the classroom kind of thing. But then I'm working on a popular level book. This course is not designed, I should say, for physics majors. I've had all sorts of history majors and English majors and you name it have been in this class. It's designed for anyone who's interested in time and wants to talk about it. I'll talk a little bit about math, so, don't be scared. It's all about the nature of time, and we talk about time from a whole wide variety of standpoint. That's my little plug. More to come.
More to come, but just, if you don't want to miss it, then drop us an email, and of course, follow us on all the social media links that we will advertise at the end of this. Right, so number 3, done. Number 2.
Number two is the DART mission. NASA successfully slammed a spacecraft into an asteroid and nudged its orbit. Why was this important? If you've seen any number of Hollywood movies, most recently Don't Look Up, the Earth has been hit by asteroids and meteors and things over the years. We're pretty sure that's what wiped out the dinosaurs. And, every once in a while stuff comes near Earth and we get a little nervous. And we have groups that track them, government organizations that track this stuff. But we want to know, could we actually, if we really had to, like if we saw one coming, could we send up a rocket and do something to nudge it into a different orbit so it went away from us? And at least proof of principle, NASA was able to do this. I mean, it's not like it's complicated in a physics sense, right? You've got something in a particular orbit, throw something big at it and cause a force to push it into a different orbit, and voila, you're all done. Of course, the big thing is the engineering. The engineering is tremendous to be able to do this. And that's what they did. The asteroid was called Dimorphos, I believe. They shot a satellite at it and basically had the satellite crash into Dimorphos and changed its position.
Indeed. So we should say that this asteroid wasn't actually a threat to Earth, but NASA launched a probe in November 2021, which they crashed into the asteroid in September, and confirmed that the mission had been successful in October 2022.
So, by the way, you should feel safe because, assuming we don't wipe ourselves out, from nuclear war or climate change, we may be able to save ourselves from an asteroid.
Whoa, that's comforting. I was just going to say, if you do want to Google the DART mission, you might want to do it actually, because it's quite fun. I don't know if you've tried it, Ian.
I have done that, yes.
A cute little effect pops up on Google if you do that. I shall say no more about it.
So Dimorphos actually is part of a binary asteroid system, an asteroid that orbited another asteroid. So it was not one that was like on course to hit Earth. What DART did is it crashed into Dimorphos, and so basically they, before it crashed in, they were able to track Dimorphos's orbit around its parent asteroid, and it had a very well-defined period. Then they looked at the period of the asteroid after. The period of an object in orbit around another object is proportional to the distance it is from that object. What we're interested in is changing the distance of the object. So what they did is they crashed into Dimorphos, and they were able to see after this that the orbital period had changed by 73 seconds. Oh no, I'm sorry. It actually altered it not by 73 seconds, by 32 minutes. Sorry. They wanted to alter the orbit by at least 73 seconds, and they altered it by 32 minutes, which is about 25 times the benchmark. So we know that we can confidently move things. Whether we move it into the right particular place and get it to where we want it to be, that's for the next mission. But we know we can actually move it.
I was just going to give you some stats. So the impact dug up 1 million kilograms of surface material. So I'm just looking at this lovely picture from the European Space Agency, which I absolutely will link to on the podcast page, fqxi.org/community/podcast. But this is to illustrate that Dimorphos was 160 meters in diameter, which is comparable to the size of the Colosseum in Rome. And so they've got this absolutely lovely, lovely image of the Colosseum with this asteroid sort of hovering over it, which I'm sure would be very, very terrifying for Romans.
Oh, God, that's really... that picture almost looks like a Magritte painting.
You don't want that picture to just get out there without any caption or explanatory text. Look. People are worried about wormholes being created, but this could cause much more panic. Good news, it's not. As you say, hopefully we will be protected from future actual threats from asteroids thanks to this kind of mission.
Yes, and I'm trying to remember, how big was the one that wiped out the dinosaurs? I'm trying to remember.
It was about 10 kilometers, so...
The asteroid that DART bumped was not insignificant in the sense that it wouldn't wipe us out, but it would cause some pretty serious damage if it did hit Earth, like real serious damage.
Well, we don't have enough to worry about as it is. At least that's one thing we can worry about slightly less. We're a little bit safer. I'm impressed that it got to number 2 on your list.
Well, here's why. It's the first time that humanity has altered the orbit of a natural object in space. Like, ever. Like, we've never done that before. That's crazy. I mean, yes, it's a small object, but we have altered the orbit, some object in space. That is nothing to sneeze at. It's a big thing for humanity to do. Think about it this way, right? Imagine you are an alien species, okay, and you are observing this distant star system, okay, and you have really, really advanced telescopes and things, so you can see little things like Dimorphos, right? But then you see this little asteroid, and it's got another asteroid orbiting it, and then you look, and all of a sudden, the orbit's different, but you don't see any reason for that. You're like, how'd that happen? And your own conspiracy theorist would say, oh, there must be aliens. And in that case, there would be. There'd be humans.
See, this tells you something about the different ways our minds work. That story went in a much more benevolent, sweet direction than I thought it was going to go. When you started off about the alien civilization, I thought they were coming to invade and we were going to send out this mission to sort of destroy or deflect them or something. But no. See, now I'm imagining that we've nudged it onto course to hit some other planet with intelligent life, and those aliens are now going to come and take their revenge and hover over the Colosseum. It's going to go from Armageddon to Independence Day. It's just, yours was much nicer. You're much more optimistic.
No, I'm not optimistic. It's just, I was thinking something more along the lines of a Douglas Adams book where, we just totally without realizing it, just wiped out an entire civilization, and it was like, we have no idea that we did it. We're just like, oh, sorry. But anyway, I do believe that there's intelligent life out there, but I don't think we're ever going to meet them, ever. Like, the vast distances over which people have to travel to get places in the galaxy. I don't think we're in danger of being invaded. Let's just say that.
Anyway, that was number 2.
Yeah. All right. Drum roll. We have a tie for number 1 because I have to be controversial, but the theme is the same. So number 1 is fusion. Okay, we have to talk about fusion results. But there are 2 fusion results to talk about. One that everybody's talking about, and one that no one's talking about. So we'll start with the one that everyone's talking about, and that is that the National Ignition Facility at Lawrence Livermore Laboratories achieved the first nuclear fusion reaction that produced more energy than was put in to create it. So we actually got a net gain in energy out of this fusion experiment. That's a huge thing.
I was just going to say, enough energy to boil a few kettles. And I have noticed some of our colleagues who are not British found that a not very illuminating analogy.
It's a pot of tea.
Regular listeners to your countdown will have known this was coming because it's been threatening for a few years now, and you did promise at some point, I think, you did say that if they ever do get more energy out than they put in, it would be number 1, and you have been consistent, so well done.
So the funny thing is that now that you mention it, I remember saying that, and I remember saying exactly that if they ever get more energy out than they put in, I will make it number 1. And I did make it number 1, but I forgot I said that. So it was purely by accident. I made it number 1 because, wow, yeah, it really was number 1. So I guess it's good that I made it number 1 and didn't make it number 3 or something.
Especially because I'm sure they only did this to get to number 1 on your list, Ian. They were listening and they knew that they had to step up. And they did.
$3.5 billion just to get to be number 1 on my list.
It's tough to get on at the top of this list.
Let me just give the background on the National Ignition Facility. So that's part of Lawrence Livermore National Laboratory. And one of Lawrence Livermore's reasons for existing is they are tasked with making sure that the U.S.'s nuclear arsenal of weapons is in good shape. Those weapons have to be maintained because if you don't maintain them, they pose dangers. The National Ignition Facility is part of that. See, in a nuclear bomb, so in a nuclear bomb, you actually have fission that occurs. There's a fission reaction. But they're interested in understanding the fusion end of things, right? Because there are a lot of weapons-related reasons for it. I don't want to get into the nitty-gritty of that. Its purpose is not to come up with a fusion reactor for everyday use, for powering our homes and things like that. And that's a very important distinction and is partly why this is a tie.
Can you just remind us about the difference between nuclear fission and nuclear fusion?
So nuclear fusion is what actually powers the sun. So in nuclear fusion, you have particles that merge together, they fuse together, hence the word fusion. So the sun is mostly hydrogen and helium, but there's fusion reactions that occur in stars that starts with hydrogen, and then you can get helium out of it, and you get heavier elements. You can go all the way up to iron. So that's what fusion is. You're fusing elements together to create heavier elements. Fission is the opposite. So fission is if you take something like uranium, and we talked about this today too. So you take uranium and you have, say, uranium-238. Well, the nucleus is unstable because even though you've got all these extra neutrons on there, it's not enough to overcome the electrostatic repulsion of the proton. And so you get chunks of the nucleus in uranium that breaks apart. That's fission. So fission is breaking nuclei up. Fusion is gluing them together. Because in both cases, energy is released. Now, the thing about fusion, the reason fusion is of interest is there's lots of problems that come with fission. We have nuclear power plants, but we know that nuclear power plants can be problematic. Chernobyl, anyone who lived through the 80s remembers that, or anyone who lived 10 years ago, and remembers Fukushima. We detected radiation from Fukushima here on the east coast of the United States, which is virtually the other side of the planet. Fukushima was not even as bad as Chernobyl. There's still area around Chernobyl that is contaminated, and you're not really supposed to go anywhere near there. So fission power, while environmentally friendly in one sense, can be problematic in another sense. Plus, you have all this extra nuclear waste that you have to do something with. Well, nuclear fusion, if we could create a system where we could achieve nuclear fusion, where we glue these things together and release energy in the process, we wouldn't have the problem, because the radioactivity is what's dangerous. And you don't have that in a fusion reaction. It just gives off energy, and you just get nice clean energy out of it. But with that said, the National Ignition Facility, that's not their business. Now that they've achieved this and they've gotten more energy out than they put in, they're not going to create a power plant or try to understand how to make this cheaper or anything like that. You're not going to see anything practical in the way of a nuclear fusion power source come out of this work.
And how exactly did they achieve this fusion result?
So they used massive lasers to basically control these particles and squish them together. The way they did it is not practical for scaling up. It's a huge, huge facility. Like you said, the amount of energy they got out of it is enough to make a few pots of tea or coffee. In order to make fusion a viable energy source, we have to find a cheaper, smaller way to do it. We have to be able to get energy out now that we've proven that it can be done. This is the first time humanity has ever actually created a nuclear fusion experiment that produced more energy out than was put in. That's a subtle point, because we've had experiments, you could say they achieved nuclear fusion, but the amount of energy you had to put in to get that fusion to happen was more than the energy you got out of the fusion actually happening. This is the first time where that is not the case. This is the first time where we got more energy out than we put in. We put in a ton of energy. We came out in the black as opposed to being the red.
So I'm taking this from the BBC website, and it says the National Ignition Facility, as you mentioned, or the experiment costs $3.5 billion. It puts a tiny amount of hydrogen into a capsule the size of a peppercorn. You spoke about the lasers that are used to heat and compress the hydrogen. It's a 192 beam laser, and the laser is so strong it can heat the capsule to 100 million degrees Celsius, hotter than the center of the sun, and compress it to more than 100 billion times that of the Earth's atmosphere. So they announced that the laboratory's lasers had input 2.05 megajoules of energy to the target and had then produced 3.15 megajoules of fusion energy output. That does sound good. I know that you've made this a joint winner, and so I think you might answer this question after you've talked about the other joint winner. But I think this hasn't come up on a lot of lists. One of the reasons might be that, people have pointed out that even though, as you say, it cost $3.5 billion, it only produced enough energy to boil about 15 to 20 kettles. And although it got more energy out than the laser put in, it took quite a lot of energy to get the lasers to work. There is a cost there.
I just want to say, I think the holy grail of fusion research has been to get more energy out than we put in. And so just proving that it's possible that human beings could actually do this, because we know the sun does it every day, but to prove that human beings can actually do this, that's a big deal. I also think it's not on other people's lists because it literally just came out. So I think that's part of it. But yes, there are going to be skeptics. No, I've had people at work, friends in other departments who are not physicists, who are like, this is going to change the world, blah, 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 blah. I don't think this particular result will, only because this particular experiment is not scalable. We can't run a city on this. It'd be crazy. It's just not practical to do that. However, the point is that the fact that we can do this at all is important. So then the next step is to find a way to achieve fusion with less money, right, and less infrastructure, so that we don't need some massive facility to get enough energy to boil some water for tea. And that's where this next group comes in, and this is where I'm going to get a lot of flack. I know I'm going to get a lot of flack for this one. So there is a group out of Oxford in the UK. They've gone partially commercial. So they're actually called First Light Fusion, but they grew out of an Oxford laboratory. And they have demonstrated a way of creating nuclear fusion using a projectile. They basically shoot things. So instead of using a laser to squeeze something to a very small level, they call it projectile fusion. It's a little bit more cost efficient the way they have it, and they have developed this new sort of technology that has been demonstrated to actually produce fusion. It does not produce more energy out than was put in yet, right? So they have not achieved what the National Ignition Facility has achieved. But they have produced actual fusion. Now, this is where things get a little tricky. So they're a commercial enterprise. Their results were confirmed by the UK's Atomic Energy Agency, or whatever it's called in the UK. The thing is that because it's commercial technology, the details are a little thin. They talk about their target. They have a fuel capsule, which is similar to the National Ignition Facility, where you had a fuel capsule, and the whole idea was that you were squeezing it to get fusion going. But they have this thing that they refer to as an amplifier in their system, which basically focuses shock waves. So when you get a collision at these speeds, you get shock waves. And so you're using shock waves, and then they channel the shock waves, which are pressure waves. Those pressure waves are used to drive the fusion reaction in this thing. And they have teamed up with a Canadian group called the Canadian Nuclear Laboratories to design a system for extracting tritium from a reactor. They're basically going to build a 60 megawatt power plant as a pilot project for this projectile fusion technology. They're estimating it's going to cost about $570 million. It's a lot of money. But it'll produce, if they're correct, about 2 kilograms of excess tritium per year, and that's where the fusion would, you're basically creating tritium, which is a version of hydrogen. Because the stuff that happened at the National Ignition Facility is simply not scalable. But this could be scalable. And that's where it's interesting. And the fact that they have enough, that they've actually achieved fusion, even though it's not fusion enough to make spare energy, the fact that they achieved fusion at all is an important result.
I can't believe that you have left out the most interesting parts about First Light Fusion, and that is that their technique was inspired by the pistol shrimp and its bubble shooting underwater, because they snap their claws together at incredible speed, creating a shockwave and squirting a jet of water forward at up to 60 miles per hour. So fast that the water itself gets vaporized as it shears against the still water around it, creating tiny bubble cavities. I don't know, I thought that was very exciting. I mean, come on, this means that our number one is actually, it's a biology story. It's about a shrimp.
I'll be honest, I missed that somewhere. I've read all these articles about them, but I missed the shrimp story. That's pretty cool.
Yeah, I assumed that was why you chose it as number one. But what would you say if I told you that when this story came out, not the First Light Fusion story, but the National Ignition Facility story, and it was everywhere, there was another outcry amongst physicists, and there was also the claim that there should have been more of an outcry about this and the headlines associated with this than about the wormhole story, because it's so misleading.
I firmly disagree with that. I understand why people are upset about it, because I have seen a lot of people who are not physicists who are like, oh my God, this is going to solve, global warming. Oh my God, this is great. And yeah, it's not going to do that. However, they never made any claim that they were out to do that. From the very beginning, they said, We are in this because we're a weapons lab and we're doing this for those purposes. They never made any bones about that fact. And their result is solid science. They got out more energy than they put in. Period. End of story. That's an important result in and of itself. That's huge. It's the first time human beings have ever done that. Okay, sure, it cost you, a bloody fortune to do it, but you did it. That's a huge result. And they never made any bones about that. They've always been very clear. We're in this for one purpose, and when we're done, we're done. So, yeah, I don't think it was blown out of proportion. I disagree with those people.
So how about this? You get a fusion reaction thingy going, perhaps with this projectile thing from First Light Fusion. Fire it through a wormhole, comes out the other side as a pistol shrimp, and collides with an asteroid and saves us from annihilation, like the dinosaurs.
Now that is a Douglas Adams novel, I'm sure.
With that, congratulations to the two fusion teams, the National Ignition Facility Group and the scientists at First Light Fusion, for coming top of FQxI's list of the biggest physics advances of 2022. More information about their work can be found on the podcast page fqxi.org/community/podcast. Well done again to Mark Kasevich at Stanford University and colleagues for demonstrating the gravitational Aharonov-Bohm effect, and to the scientists and engineers behind NASA's DART mission 2. That's all from us at FQxI for now. Though I'm going to let you into a little secret, we do have some exciting new developments to share in 2023, like Ian's Nature of Time course that we mentioned. So if you haven't already, make sure you subscribe to the podcast on Apple or Spotify and follow us on your favourite social media platforms so you don't miss any big announcements. You'll find us on Twitter and LinkedIn at FQxI. You'll find Ian at Quantum Moxie on Twitter. We're also at FQxI Physics on Pinterest, where I have created a board for the countdown and collected all the stories on this list. We're also at FQxI Physics on Facebook, Instagram and TikTok. And I'm on Mastodon at FQxI at sciencemastodon.com, and Ian is at Quantum Moxie at sciencemastodon.com. So you really have no excuse for not connecting with us somewhere. And of course, you can always still email me at podcast@fqxi.org, and certainly please do drop me a note if you would like to be notified when we have a bit more information about Ian's new online course on the nature of time. So thank you once again to Ian Durham, and to you for listening. I've been Zeeya Merali, and all that's left to say from everyone at FQxI, we wish you all the best for 2023.
Happy New Year!